The multilayer perceptron that we saw earlier can be generalized or is an example of a feed-forward neural network. So both the perceptron and the multilayer perceptron are feed-forward neural networks. So feed-forward neural networks are the neural networks in which the connections don't form a cycle. That means that the nodes, so what we have in feed-forward neural networks is that the nodes from one layer are only connected to nodes further up in the network. So they're only connected to nodes in different layers. And they only move forward. So the input layer can only be connected to some hidden layer or to the output layer. Again, each hidden layer can only be connected to the hidden layers that come after it or the output layer. So we don't have any connections in feed-forward neural networks. We don't have any connections between nodes in the same layer, and we also don't have any backward connections. So we can't have, for example, this node be connected to this node here. And in feed-forward neural networks, the information only moves from the input to the output. So it starts here, it goes through the hidden layer. We could have multiple hidden layers, so it can move through them all the way to the output layer. The goal in training feed-forward neural networks or any neural networks is to find the weights for the connections between the nodes. The goal is to find the weights that will maximize the classification or regression accuracy. So what we want is that if we classify so if we want to use the neural network to classify some data, we want this classification to be as accurate as possible. The steps we take in training a feed-forward neural network is to first create the feed-forward neural network, and then to initialize all weights to some small random number. For example, it can be 0.2 or something like that. So something close to 0 is what we want. And then we take each training example that we have and we propagate this example through the network and compute the output of every output neuron. So we basically classify, or let's say if we're using the network for classification, we classify this training example and we'll see whether the output that we get is the same as the output that's expected. That's this y here. And then we propagate this error backwards. So we look at the output. If this is wrong, we propagate this error backward through the network. And for each neuron, we want to know how far away it is from the value it needs to have to give us the correct result. And then based on this error, we want to update each weight so that we get correct or we get closer to the correct classification. The thing that we do here actually is that we compute how different the result that we get is from the expected, and then we want to minimize this error. We keep repeating this, so we do this for each training example. We want to know what's the way, whether the current classification is correct, and how and if it isn't, we want to propagate the error backwards and see and update the weights. In doing this, we want to minimize the loss function. This loss function is actually the difference between, or the discrepancy between the expected output and the output that we actually get. We keep repeating this until we converge. That means we stop when some stopping criterion is met. That can be, for example, if the error doesn't change a certain amount of time, then or doesn't change enough, or doesn't decrease enough, then we can stop. Or we can also say that if we don't find some type of convergence, so if the network can't achieve the lack of change that we want to have, then we want to stop after, for example, some given number of passes of the training set. The updating of weights during this training process depends on the learning rate, which determines how fast the neural network learns new information, or how aggressively we want to change the weights during the training. If we have a high learning rate, then so in this graph we can see how the loss function will behave, so how this discrepancy between the expected results and the actual results behaves depending on the learning rate. If we have a very high learning rate, then the loss can become very large because we want to change the weights too much. If we change the weights too too little, so if the learning rate is too low, we can see that the change in this loss function is very slow. So we go towards some kind of solution, so we do get a lower and lower error, but this happens very slowly, and it would take very long to get to the correct result. If we have a high learning rate, then maybe we can't really get to some very we can get the loss as low as we want. The appropriate learning rate is the one that makes the loss behave in the way as shown on this graph. So it changes, it decreases pretty quickly. And as we do more and more passes of the training set, we get a very small discrepancy between the expected and actual outputs.